Hi, my name is Kristen Lavery. I'm the Assistant Director and Business Manager for the Leonard Gelfand Center for Service Learning and Outreach, and I'm talking to Dr. John Alison, who is an Assistant Professor in the Physics Department at Carnegie Mellon University.
Thanks, yeah, it's great to be here.
So we want to hear a little bit more about what's going on in your lab. What exactly are you building?
Right, yeah, so sort of an easy way to think about it is we're building a bunch of very radiation-tolerant digital cameras. So we're going to build about 5,000 of these total. And that's all being done in campus here in Wien Hall on the 8th floor.
So these digital cameras, I know they relate to a larger project.
Right.
So how does this project relate to the science being done at the Large Hadron Collider?
Right, yeah. So, I think a lot of people know about the Large Hadron Collider, the LHC. And so what we're building is actually an upgrade to one of the detectors there. And so the first question you might ask is, why do we need an upgrade? And so it turns out that the current detector we have now is beginning to fail, right? And so the idea is we have these actually the incredible detectors there. You can think of them as sort of transparent lead bricks, okay? And what happens is the particle comes into the lead brick and it slows down. And when it does that, it emits light. So that's one of the things that basic physics tells you. And because these lead bricks are transparent, the light propagates through them, and we could put photodetectors or light detectors at the end of the bricks. And by measuring how much light we see, that correlates very well with how much energy the incoming particle had. And so this is a great way to measure the energy of particles at the LHC. Now the problem is these bricks get damaged by the radiation. So you can imagine when the protons collide, they give off a lot of ionizing radiation, and that is actually damaging these bricks, and they're becoming less transparent. Okay, and in fact, some of them, for the ones that are in the regions where the radiation is the highest, we're only seeing about 1% of the light that we saw when we first started. And of course, the amount of radiation damage goes like the amount of data that you collect. And in particular, to study the Higgs boson, we want to collect a lot more data. So that means more radiation damage, and that means these detectors are just not gonna function for the higher intensity data that we want to take. And so what we're going to do is build a new detector that will replace these sort of transparent lead bricks, and that's going to happen here at CMU.
Interesting. And has anything like this ever been done before?
Right. Yeah. So that's an interesting question. So the way that the way that these experiments work is there's sort of, you can think of them as like two flavors of detector. There are detectors that are very close to the interaction point where the protons collide. And these detectors just measure the positions of the particles. So they actually don't stop the particles. The particles go right through them, but they leave little energy deposits. And we have a whole series of these detectors that are layered. And sort of by connecting the dots, we can infer where the particles went. Right, so that's the one type of detector. Those are often called tracking detectors. Again, they don't stop the particle, but we can infer where the particle must have gone based on the energy it leaves behind. Then the second type of detectors are what are called calorimeters. And so a simple way to think about these is these detectors stop the particles, and they measure how much energy it took to stop them. So these like transparent lead bricks were a type of calorimeter, right? The leads really stopped the particles, and the light measured how much energy it took to do that. What's interesting is that these detectors typically look very different from each other, right? One, the tracking detector is really like a digital camera, where the calorimeter are these fancy transparent lead bricks. And so what we're doing now is we're kind of merging the two, right? So we're building this detector that's really meant to stop the particles and measure how much energy, but we're using the technology of the tracking detector, the digital cameras. And there's a couple reasons for that. One is that the digital cameras are very radiation tolerant. And so that's something that we need, that was the whole problem with the current detector. And so it's almost like a hybrid detector that we're building. We're using just regular lead that's cheap, and we don't care if it gets radiation damage to stop the particles. And we have these fancy digital cameras that to measure the shower or the particle as it stops.
So New and improved, essentially.
That's right. Yeah. I mean, another way to think about it is, we're going from the current detector that sort of just tells us a number, like how many photons did we see, to a detector that's really imaging this whole shower in it's almost like a high resolution 3D movie, right? So we'll have, the current detector reads out something like 80,000 numbers, and this one will have over 6 million numbers. So it's really, it's an example of big data getting much, much bigger.
Moving forward in your research, what are the main challenges with this project?
Yeah, so the one of the issues is just building all of these. So we need to cover a lot of area, so that the particles that are going to come out with a lot of energy, and so it takes actually a lot of material to stop them. That's one of the reasons why these detectors are so big. To deal with that, we just need a lot of area that's sensitive to the shower. So we're going to build something like 600 square meters of silicon, which is really, that's an unprecedented amount. And so, I think the real challenge is going to be just scaling up. So the way that we're going to do this is we're going to build these sort of 8-inch modules, right? And we're going to make a bunch of them. They're going to be hexagons. Hexagons are nice because you can tile the plane with them. And so we're going to make, a bunch of these, 30,000 total. And that will allow us to tile the plane. So we'll make, sort of planes of them. And we'll make about 50 different planes, and we'll stack the planes to make sort of a full 3D detector. So the big challenge is just going to be, we think we understand how to make one of the modules, right? And then we need to be able to make, about 24 a day, right? And so there's a lot of challenges with that. The biggest challenge is we need to make about 24 a day, but it takes a few days to make a module, because there's gluing processes that have to happen, where it takes overnight for the glue to set, essentially. So that means at any given time, we'll have about 100 modules in some stage of being built, right? And one of the big problems is, or one of the big worries that we have is, if we introduce a problem in assembly on day 1, we won't be able to catch it with the electronics until day 5. And so that could compromise 100 modules. These things are like $1,000 each, right? And so, we just can't afford to have problems. We can't afford to have problems that we don't catch right away. And so one of the things that we're really worried about is, how do we catch problems with our assembly process before we have the full electronics available to test the module.
Well, it sounds like you really have your work cut out for you there. We were also speaking to a student in your lab as well, Stuart Johnson, who's involved in your clean room set up there. And it sounds like everything in your lab has to be spotless, no small particulates. And with what you just described, I can only imagine how the tiniest piece of dust could potentially cost you thousands of dollars and time.
Right.
As well. Well, Dr. Alison, we wanted to say good luck in your project, and thank you for coming to talk to us today a little bit about your research.
Yeah, thanks. Good. It was great talking to you, and you guys should come back when we start making the modules and see it in operation.
Definitely. Thank you for the invite. And I want to ask our audience out there to please be sure to check out our 360 lab tours.